Good morning, future presidents. Excellent. Okay, today we are talking about collisions. So remember, we've already talked a little bit about collisions when we studied momentum. So let's remember that a collision is an interaction between two objects where forces are exchanged, an action-reaction pair. Okay, so there's exchange of momentum and potentially energy between the two objects during a collision. So let's remember our conservation laws. So momentum is always conserved. Awesome, thanks. Okay, momentum is always conserved. Okay. We know that because the forces always act in action-reaction pairs. So whenever a force is acting for over a period of time on one object, the opposite force is acting for the same amount of time on the other object. So momentum is always conserved in the collision. Okay. The other one is the total energy. Is always conserved. But, okay, there's a big but on this one. Okay, total energy is conserved, but not necessarily as kinetic energy. Okay, and the most common example is that we can lose kinetic energy to thermal energy in collisions, or to elastic energy for when we deform objects. Okay? So the energy isn't lost; it's just moved to a form that is no longer kinetic energy. Okay? So momentum is always conserved. Total energy is always conserved. Okay? But the kinetic energy is not necessarily conserved in a collision. Okay. So, given these two conserved quantities, we can define three types of collisions, and we're going to look at those in a lot more detail today. So there's three categories. Okay, the first one that we want to define are called elastic collisions. Okay, these are a special case. They're actually an ideal case. It is very difficult to have an elastic collision in the real world, but it's still a very constructive example. Elastic collisions are defined where kinetic energy is conserved. Okay, momentum is always conserved. In elastic collisions, kinetic energy is also conserved. Okay, so that means that there is no energy lost. I put lost in quotation marks because energy is we know the total energy is conserved. By lost, we mean it's being changed to other forms. So no energy is lost to other forms in the collision. Okay, that's our definition of an elastic collision. I bet you can guess the next one. Okay, inelastic collisions. Inelastic collisions are collisions where the kinetic energy is not conserved. So that means that energy has been transformed to some other form. So it's usually heat that we are talking about. Okay? But inelastic collisions, okay, significant energy or specifically significant kinetic energy, is lost during the collision. Okay, so kinetic energy can be lost through a number of different means. It can be lost through heat, which is the most common form. It can be lost through sound, and the next one, which is also common, is mechanical deformations. So for example, if you have two cars that collide and their bumpers collapse, okay, then that's a mechanical deformation. It takes energy in order to make those deformations in the bumpers. Okay? So these are ways that the energy can be transformed from kinetic energy into other forms during the collision. Okay, so any real-world collisions, okay, between two objects are in fact always inelastic. Okay? The idea of an elastic collision where no kinetic energy is lost whatsoever is an idealization, okay? But it's also it's a very instructive idealization. And it's an okay approximation in a couple of cases. Okay. Okay, the two cases are when the objects are not permanently deformed, or I should say the two requirements to get an almost an elastic collision are that the objects are not permanently deformed, and the second is that the objects do not stick together. And we're going to talk about this in 1 second. Okay, if the objects don't stick together and the objects are not not deformed in the process, then it's a pretty good approximation to use to assume it was an elastic collision and kinetic energy was lost. Okay? You can see already for these two, I'm going to send these two balls in towards each other, and you can see that they rebound with less energy than they had initially. Their speeds have decreased. Okay? But it's still not a horrible approximation to say that this is an elastic collision. Okay? The balls were not deformed, and they didn't stick together. Okay? They did go out with significant velocities, so at least they remained, they retained most of their kinetic energy during the collision. Okay? So let's define our third category. So we've got elastic collision, we've got inelastic collisions, and the final category is just a modification of this last one, which is perfectly inelastic collisions. And so this is a special case of inelastic collisions. Okay? It's the case when two objects collide and stick together. So the colliding objects stick together in the collision. So you can think about maybe two clay balls that are incident on each other, okay? And they stick together, so then they move off as one object. Or you can think about a car collision when the cars come in and hit each other and the bumpers lock, okay? And so that they stay connected after the collision. Okay? Colliding objects that stick together, we call that a perfectly inelastic collision. And the reason we separate this out from just regular elastic collisions, of course, is that it's a little bit special. In these cases, the maximum kinetic energy is lost. course, by lost, we mean it's transformed into heat and sound and other forms, okay? And potentially even all of it. Okay, so quick example of that. Okay, and we're going to talk about this more, but just to explain why that's lost. So imagine we've got these two balls. Once again, they're going to roll towards each other and collide. But now imagine they were made out of something sticky like clay or maybe lead, where they're going to completely stop. Okay, they hit each other and they stop. Okay, so they're coming in with kinetic energy. They hit each other. In order to conserve momentum, they're coming opposite directions, right? They're going to stop when they collide. All the kinetic energy is lost in that collision, okay, because they've stuck together. Okay, so that is the extreme case for an elastic collision, where you lose the maximum amount of kinetic energy. Okay, but you're still conserving momentum in this case. So yeah. Yeah, in this case, there's a little bit of sound. You can hear a little sound that's traveling out, but that's pretty small. In this case, most of the energy would go into thermal energy in the two balls, and we'd be hitting them up. Yeah, exactly. So, okay, so yeah. Okay, so the question is, if you've got two objects that come together and they partly stick together and part of them don't stick together, right? So would you still call that perfectly inelastic? Yeah, you would call that perfectly inelastic. If they're still sticking together, then as a whole, and the most kinetic energy is lost. But in that case, if they are partly sticking together and partly not, then that means you've deformed them, right? So that means part of the energy that you've lost, part of the kinetic energy you've lost, instead of going into heat or sound, it's gone into actually physically changing the shapes of those objects. So yeah, good question. Yep. Yes, so we're going to come back and talk about this some more. So the question is that if they keep moving after they stick together, is there still the maximum kinetic energy lost? And so one case of that would be, let's say I rolled this one in and this one's at rest, right? I roll it in and they stick together like that, and then they both go moving off at a lower velocity. In this case, we'll actually do this case in just a few minutes, but you'll see that the kinetic energy is significantly dropped here. Okay? The reason they're still moving, though, is because they still have to conserve linear momentum no matter what. So they can't come out of this collision without having some motion. Okay? But the amount of kinetic energy they lost is the maximum amount they can lose and still conserve the linear momentum in this case. So that's why this is such a special case. Yeah, good questions. Yeah, one more. Is any work done in a perfectly elastic collision? That is a great question. Yes. Normally we ignore that because when you think about a collision, okay, and in fact, these are great questions. They're anticipating the rest of our lecture. So when you think about a collision, when these two objects are hitting each other, they are starting to transfer force back and forth. And when they're transferring a force, that's normally because they're elastic to some level, and so the surfaces are deforming. Right? And so during that time when their surfaces are deforming, right, they're exerting a force back on each other, and when they're rebounding, as that surface undeforms, right, it's acting over a little bit of a distance while it's coming out. So there is work that's being done, but we're seeing that as coming out of that in terms of the energies afterwards. So energy's been transferred. It's been transferred because there's work done. Okay? And then momentum. Okay, and the momentum's been transferred because there's impulses, forces acting over time. Yeah, good questions. Oh my gosh, I'm happy. Okay, so let's look at our first example in a little bit more detail, which is going to be the simple example of just a ball hitting a surface. So like a ball hitting on this. This is a glass plate. I could bounce it off of this, but it bounces. Okay, this is a steel cylinder, so it's just different surfaces. Okay, this is just a bouncy rubber ball, of course. Let's draw a picture of what's actually going on in a little more detail when we have a ball hitting a surface like that. Okay. Let's draw it going sideways, just so we can not worry about gravity for 1 second and get to just the heart of what's going on during the collision. Okay, so this is a ball hitting a wall. Okay, pretty basic example. Okay, this is also going to let us define a couple of quantities that we're going to talk about. So here's our wall. Okay, and here is our incident ball. It's got some kinetic energy that's coming in, and we're going to call this the collision energy, which is the energy that it has before the collision. If we were dropping the ball from up here, then the collision energy would be its kinetic energy just the instant before it hit the table. Okay. So that is the before picture. Let's draw the middle of that collision. So this is progressing in time. Okay. So the ball is hitting the wall. The wall's exerting force back on the ball. And a couple things happen during this collision, and it's usually too fast for us to actually see. So let's say this is where that wall was initially. So a couple things happen. First off, that wall will get slightly deformed. Okay, I've greatly exaggerated it here, okay, for this illustration. But the ball's incident on the wall, it's exerting a force on the wall, so the wall gets bent a little bit. That ball, okay, here is our ball, and I've shown it as being deformed. It's gotten flattened out. Okay, that, of course, is also an exaggeration unless you've got a very squishy ball. Okay. So at this point, we're looking right at the instant when the kinetic energy is equal to 0. Okay, so that ball has come to rest. It's come to a stop. Okay. And so we're looking just right at that instant when the ball has come to a complete stop against that wall. And there's a couple things that are going on. First off, there is elastic potential energy in the surface. So there's elastic potential energy that's stored in that surface because we've deformed it. So that's just like the surface of a trampoline. Okay? Or you could think of the walls acting like a spring. So the balls come in and compress it a little bit. Okay? So there's energy stored in there. 1 second. Okay? There's also elastic potential energy, EPE, elastic potential energy, okay, in the ball. Because that ball is acting the same way. If you squish it, right, it's acting like a spring pushing back on it. So it takes work in order to compress it. Right? And when you do work on it like that, it's got potential energy that is released when it lets go. And there's one more thing I want to point out here, which is some balls, like a tennis ball or a basketball, are hollow. So they have air inside of them. So there's the possibility when that ball, if it's hollow, got air inside of it, that the air gets compressed. Okay? And when that air gets compressed, we'll see later that it also means that that air gets heated. Okay? So we've transferred that kinetic energy of the incoming ball into a couple different forms. We've changed it to potential energy in the wall if the wall is giving away a little bit. There's elastic potential energy in the ball as the ball deforms. Okay? If you've got a good ball, it won't be a permanent deformation, and so that means we'll be able to get that energy back. Okay? And there's also energy that goes into the air when it gets compressed. So, yeah, you had a question? I got it? Okay, great. So, so that is the instant when the ball comes to rest. Okay? So now during this time, of course, the ball is exerting a force on the wall, and the wall is exerting a force back on the wall. So there is a force acting over time on that ball. It's directed in this direction. Okay, so there's an impulse that is being imparted to that ball. Okay? So we would have to be able to study this very carefully in order to know what the forces are as a function of time, okay, for this collision. Usually we don't have to look at that in detail. So we can look at it from what's the situation beforehand and what's the situation afterwards, and we know how much the impulse, okay, has been transmitted to that ball. So we'll talk about that more in just a second. So, but let's go on to the next case, the third stage in this, which is now the ball has rebounded. Okay, so let me draw that over here next to this. Okay, so here's our wall. It's returned back to its initial state, which means it's released the potential energy, the elastic potential energy that it had stored. Now, if the wall actually gets deformed, so if you throw it hard enough that you make an indent in the wall, okay, then that's a permanent deformation, which took energy. And so that means there would still be some energy that was taken back from that, from the ball. Okay? But normally we would get the wall that is reformed, and the ball comes back out in the opposite direction, and it comes out with a rebound energy. Okay. And for any real collision, the rebound energy is less than the collision energy. Okay? But the closer it comes to an elastic collision, the closer that the rebound energy gets to the initial collision energy. Okay, so the details of these forces, okay, can be pretty complex. You've got the ball compressing, you've got the air compressing, you've got the wall that's changing shape. Okay? We don't normally think about it in all that detail, because from a more practical purpose, we kind of just want to know if we throw the ball at that wall, how fast is it going to come back at us? Okay? And we usually do that by measuring. So for a given ball on a given surface, okay, so the nature of the rebound can change depending on whether you're hitting a hard surface or a soft surface. But if you've got a known ball and a known surface, like this wooden table, or the concrete, or the walls, the plaster on the walls, then the rebound energy is just a constant fraction of the collisional energy. Okay, so during the collision, the ball will lose a constant percentage of its energy. Okay? So that means, for example, when you're looking at a bouncing ball, okay, so let's take a look at now the bouncing ball. So the bouncing ball comes in, and it loses some percentage of its energy. Okay? So remember that the potential energy that it has is just measured by its height. Okay? So if this comes down and then bounces, and let's say it loses 50% of its kinetic energy, then it will only bounce up to half the original height that it had, because it's lost half of its energy. Okay? So that means when it bounces again, it's going to lose that same fraction, 50%, and then it only bounces up to half the height that it had during the last bounce. Okay? So each bounce it's going to lose half of its height. Okay? And so, So let's draw that. So bouncing balls, they always lose a fixed percentage of the collision energy. Okay, so for the bouncing ball, that would mean that, for example, let's draw our floor here, and let's look at a tennis ball. Okay, so for a tennis ball, okay, you can see when I drop it, it bounces up. That height that it bounces up for a good tennis ball, this is kind of an old tennis ball. For a good tennis ball, that height is 56%. So it's regained 50%, 56% of its collision energy, okay, during the bounce. Okay, so that means if we start off at some height here and we drop it, so this is the initial height, we drop it down, okay, it bounces up to 56% of that initial height, okay? It hits the ground. Okay, so then on the next bounce, it will come back to 56% of that height. So 56%, that's not a very good parabola, but that's okay. Okay, bounces up again. The next one is 56%. Okay, so, and then on and on and on. So in theory, this would just keep on bouncing at smaller and smaller heights forever. Okay? Eventually, friction and heat loss are going to kick in. So let's just put some numbers for a few different types of balls out here so we can see them for comparison. Oops, that one likes to bounce. I do not know where that went. Okay, it's down there somewhere. Okay, let's look at different ball types and their ratio of rebound to collision energy. Okay, so for a super ball like that one that I just lost, okay, this ratio is about 0.81, so 81% of its energy is regained after that bounce. Okay, so that's pretty good. These super balls are a pretty good approximation for elastic collision. Okay, so let's just put some more different type of, can't find it either. Okay, golf ball. Did it roll out front? Okay, I'm just going to make this list here. Golf ball, 67%. Okay, so golf ball is pretty bouncy. Okay, basketball. Okay, it's okay, Adam. I got it. Oh, thanks. Perfect. Okay, basketball is about 0.64. Okay. Tennis ball is 0.56, so 56% of the energy. Baseball is about 0.30. Okay, baseballs are not very bouncy. Okay. That's probably good if you are on the defense, because you don't want the ball to bounce too far off of the bat, okay, for the people that are hitting. Okay, and it's probably good if you're trying to catch balls that are bouncing towards you across the baseball field. Okay, the last one I want to put on there, as I don't quite have room, so let me just write it off to the side. Nerf balls, foam rubber balls, about 0.09, so they are very inelastic during their collision. So let's look at some of these things bouncing. Okay, so this is a, so we'll just bounce them off of this. Actually, let's bounce them off the surface because it's a bigger. So this is a super ball, so it's got about 81% Probably varies quite significantly depending on the material, but you see it's going to regain most of its energy after the bounce. And you see it bounces quite a few times before it comes to a stop. Let's do an extreme opposite comparison. This one is a lead ball. So I didn't write lead on there, but lead is basically the Nerf balls of metals. Okay? Lead is very soft metal, so it deforms very easily, and it stays deformed very easily. So when I drop that on there, okay, very inelastic, okay? Zero bounce whatsoever. Okay? That's the extreme opposite. So let's do a couple other materials here. Here's steel. So steel is also metal like lead, but it's much harder, so it doesn't deform nearly as easily. Okay? So when it drops, it gets bent a lot less, for one thing, and then the deformations restore pretty easily. So see, it's very elastic collision. So it's up there with the superballs in terms of how much energy is actually transferred during the collision. Okay? In fact, this one's better than the superball, so in its bouncing. That one was probably closer to 90%. Okay, let's see, wood. Okay. Wood is a soft material, but it deforms pretty easily, so see that it doesn't bounce very well at all. If I had to guess, I'd say that's probably about a 20% energy that it regains on the bounce. And let's see, what else do we have here? We've got a bunch of different materials. Let me do glass. So this is a glass marble, which is hard. Okay? It's not as hard as a steel, but we know that glass isn't going to deform very easily unless it shatters. So hopefully I'm not going to shatter it, but as long as I'm not shattering it, it should bounce pretty well. So yeah, it's probably up there 80, 90% of its energy that it's regaining. You can see it bounces for a long time. I got pretty good aim, didn't I? Yeah, that's impressive. The surface is a little curved. That helps. Okay, so let's draw a case, which we didn't actually see there, but it's very instructive, which is if we had a ball that was perfectly elastic. Okay, so let's call this an elastic bounce. Okay, so in this case, by elastic, we mean that the rebound energy is equal to the collisional energy. So that means that no energy is being transferred to heat or to sound in this collision. Okay, so if we draw a picture of that, here is the ground. Do that a little bit too low. There is our ground, okay? Here is our ball that's going to be colliding with the ground with a perfectly elastic collision. Okay, if it's perfectly elastic, it regains all of its energy after the collision. So in this case, that would just mean that if this was the original height, that ball would be falling down, okay, bouncing back up to the original height, okay, and every time it bounced, it would go back to that original height. It's not losing any energy. Okay? So that's a perfectly elastic bounce. We already saw that none of these materials actually give you a perfectly elastic bounce, even though the steel and the glass did pretty well. Okay? They came pretty close to being perfectly elastic. Okay? But let's use this as an example and talk about the forces, and especially the impulses that are being transmitted during the collision. Okay? So let's look at the momentum of the ball. So remember, the momentum is equal to, Let me do that off to the side over here. Okay, so remember that momentum is equal to the mass of that ball times its velocity. And when we're talking about the velocity, we have to remember that the velocity has a direction as well, okay? And so during this collision, the ball comes down, and right before it hits, it has its momentum directed downwards towards the ground. During the collision, okay, it regains all of its energy, but the momentum is flipped directions. So at that point, the momentum is pointed upwards. Okay? The fact that the momentum has changed for the ball, it's changed direction, means that there was an impulse that was being imparted to it, so that the ground had to be exerting a force back on the ball. That's pretty intuitively obvious, right? So during each one of these collisions, the momentum of that ball gets flipped, okay, from going down to going back up. Okay, so let's draw that over here. So here is the initial momentum coming in, directed downwards. Okay. Now, when we are flipping it, that means we have to be exerting an impulse upwards. That's the force multiplied by the time that it's being exerted. Okay? And that impulse is transmitting momentum. Remember, an impulse is a change in momentum. And that impulse basically has to not only cancel that initial momentum that's going in, but add another amount to it that's equal and opposite in the initial direction, so that the final momentum is directed upwards. Okay. You might think that momentum is not being conserved in this case, okay, because the ball comes in, it's got initial momentum downwards, it leaves, it's got a final momentum that's directly the opposite direction. Okay? But because there's an impulse acting on it, that means there's also an impulse that's acting on the floor down here. So this floor is getting pushed downwards. Okay? It has momentum that's being transferred to it. Okay? It's such a huge mass, the floor or the earth, okay, that the velocity is so small that it's negligible. Okay, so we can ignore that in this case. But momentum is still absolutely being conserved. Okay? It's just that the velocity imparted to the Earth is completely negligible, so we don't have to worry about it for this case. Okay, so this is what we want to focus on here. Okay? There is an impulse that is being imparted by the floor. We do not know, in the case for the elastic collision, we don't know all the details about that force. That could be a very large force for a very short time. It could be a very small force for a very long time. It could be a time-varying force that's acting over a different amount of time. But we don't need to know the details. All we need to know is that in the elastic collision, the velocity has flip signs. It's changed directions, which means that we know the total impulse that was enacted. It has to be twice the initial momentum coming in. Okay. Let's compare that with now another case which we did pretty much see, which was a completely inelastic bounce. So let's call this actually the perfectly inelastic bounce. And I use the term bounce here lightly. Okay, we saw that with the lead ball. Okay. Perfectly inelastic, zero kinetic energy afterwards. Okay. Comes down and comes to a stop on the surface. Okay, so that is a ball that comes down, falls down, hits the ground, and basically gets deformed in some way, so that comes to a complete stop. Okay? So that means all the energy of that fall has been converted into both heat and sound and to deformation of that ball. Okay, so it hits and sticks. So there's no bounce in this case. Okay, let's look at the impulse acting on this. Okay, this ball, let's say that we've got balls of the same mass here, and we're dropping them from the same height. Okay, so when that ball comes down and hits, when it's coming in, it also has a momentum, which is the same as this momentum coming in. Okay? So the difference is that here is the initial momentum. Okay, the final momentum is zero because that thing is stopped. Okay? So that means we know that the impulse acting on it, so this is the impulse. I should have drew this somewhere else. Let me pull down another board for this. Okay, so let me draw that same picture. So here is our initial momentum. Okay, it's the same as the case for the elastic bounce. Okay, but in this case, the impulse acting upwards, okay, isn't restoring the full momentum going upwards, so it's not flipping the direction. It's just bringing it to a stop. So the final momentum over here is zero. It's come to rest. Okay? So that means that the impulse that's acting on it, so that's a force times time, remember? In the case for the inelastic collision, is only half as much as it is for the elastic collision. Okay? That's because for the inelastic collision, okay, it only has to bring it to a stop, so it only has to counter the amount of initial momentum that it had coming in. Okay? It doesn't have to reverse it, which means it doesn't have to add this amount of momentum to that as well. Okay? So the impulse in this case is only 1/2 of an elastic collision. Or an elastic bounce in this case. Okay, that tells us some really important things, actually. So remember that impulse is force times time. So if this bounce is taking the same amount of time as this bounce, that means that you're only getting half of the force for the inelastic bounce that you would have for the elastic bounce. So the forces are half as much. Now, it can also be the case that, for example, for this lead, right, when we drop it, it's actually deforming, right? It's bending a little bit, it's changing its shape. Okay, whereas the steel, which is really hard, is bending or deforming only the slightest a bit. Okay? What that means is when this is deforming, it takes more time for the collision. Okay? So not only is the impulse half as much for the inelastic collision, but if you're actually deforming the object during that time, the amount of time in the collision can be much larger, which means the forces can be much smaller. So that means in the inelastic collision, the net forces acting on the objects can be a lot smaller than in an elastic collision. So practical examples, okay. For example, that ball is you in your car, and this surface that you're hitting is a tree. It is much better in car accidents if the car comes to a stop, if it has an inelastic collision caused by the car deforming during the collision, than if the car comes in and bounces off. If it comes in and bounces off, then you know the impulse is twice as high, which means the forces are a lot higher. If it's crumpling, that means that the time of the collision is even longer, which means that the forces are even lower. So that's why, for example, bumpers back in the 40s and 50s in cars used to be designed from really strong steel. They were designed to bounce, right? Not to bend or break. That means they were designed to try to get elastic collisions out of car collisions, which means the forces were much higher than if those bumpers were made to crumple. So that's why bumpers on modern cars are made to crumple. It's much better to replace your bumper than, to replace your head or arms. The forces are a lot less if it's crumpling. Same idea with airbags. When you are coming to a stop in a collision, you are undergoing an inelastic collision, and it's much better to hit that airbag and have that airbag crumple over a longer time for a smaller force, than hitting that dashboard, which would be a pretty elastic collision between you and your forehead. Okay, so we will continue with collisions in a second, but are there any questions on these so far? Elastic bouncing and inelastic bouncing. No, good. Well, you know what I'm in the mood for? I'm in the mood for a quiz. Can we have the overhead? I like the excitement. Okay, if you don't have a quiz slip, raise your hand and see if you have a friendly neighbor. Okay. Anybody still doesn't have a quiz slip? Okay, I have a request from the GSIs that are grading your quizzes that they will not grade them if you do not circle your section number on them, because they have to sort those into sections. So we try to make that as easy as possible for you. So find your section on that quiz slip and circle it. Did I say that's forcefully enough? Okay. Okay, let's start. Question number 1. Suppose you're standing on a bathroom scale when you're flying in a jet airplane. I'm not sure why you do that, but okay. Let's suppose you're on a scale in a jet airplane, and for a moment the scale reads less than your actual weight. So during that moment, the scale, it is exerting an upward force on you that is A, greater than your weight, B, equal to 0, C, equal to your weight, or D, less than your weight. Okay, let's move on to question number 2. You are extremely bored during the long summer months when school is out of session, so you decide to attach a rubber, just a ball to a rubber band and repeatedly bounce it up and down vertically. Okay, So it's like a mass on a spring. When the rubber band is at its maximum stretch away from your hand, so here we're picturing you're bouncing it up and down. Okay, so we're looking at the case when the ball is at the maximum stretch down at this point. Okay. The question is, A, the ball's velocity is downward, but its acceleration is upwards. B, the ball's velocity is 0, but its acceleration is upwards. C, the ball's velocity is upwards, but its acceleration is downwards. Or D, the ball's velocity is 0, but its acceleration is downwards. Yes? You're bouncing it down, so it's, that's right. So the idea is that you're bouncing it down like a yo-yo. Okay. And you're looking at the case right when it's at the lowest point, stretching the rubber band. Okay, check and make sure your name's on that. Circle your answer, circle your section, and hand them over to the right and the left. So we'll have the GSIs come along and collect them. So. We've got both Nathans and Maxwell Adam. By the way, while you guys are getting settled, so this week's material, so today and Thursday, are the last sections we will be covering for your midterm. Your first midterm is 2 weeks from today. It's in class. And most of you guys, there's some of you that are going to be away for sporting events. You guys need to contact me probably towards the end of next week, and we will arrange for you guys to be able to take those from your coaches. And there will be practice midterm posted sometime within the next few days, so you guys can get an idea what's going to be on that. And we'll talk about that more probably next week as we get closer. So I just wanted to give you guys a heads up that that was coming amazingly quickly. 2 weeks from today. So you also will not have homework due or an essay due the weekend before the exam, so you can study. You're welcome. Okay, so let's continue on here with more examples. We're going to look at head-on collisions. Okay, so here we're imagining two objects. In this case, we're just going to look at two objects of equal mass that are basically hitting each other in a straight line. So head-on collision between two objects. Yeah? I'm sorry, I couldn't hear you. The midterm is on October 4th. Huh? Well, you get a study guide. No, you'll get an example exam, which is very close. So, and then you'll be basically responsible for all the material in the chapters, and then the material we covered in lecture. So, but for example, you will not be responsible. I gave all those graphs on energy usage and stuff. Those are mostly for your information. I won't start quizzing you on find specific numbers on that. So, okay, but we will talk about more about the exam as we get close. So let's not worry about that today. So, okay, so head-on collisions. We're going to be talking about two objects of equal mass for simplicity. For now. Okay, and we just want to compare the cases of elastic collisions and perfectly inelastic collisions. Okay, so let's start with, we'll do elastic collisions here. Okay, the first case I want to look at, okay, just to give us sort of an intuitive feeling for what collisions look like. So this is the case when one of those masses is at rest. Okay. So this is a case where we have one, let's call that mass 1. It's coming in with some initial velocity. And it's basically hitting a second mass here, which is starting out at rest. Okay? So that first one is coming in at some velocity, the second one's at rest. If we look at the momentum for the system, well, we've got this one we've got a mass, we've got initial velocity in this direction, so its momentum is in that direction. This one's at rest, so its momentum is equal to 0. Okay? So the initial momentum of the system has got to be directed off to the right in this case, okay, which is just equal to the momentum that this first one is coming in with. Okay, so these two are going to collide. So here we have them right there. So this one's coming in, it's got initial momentum. Okay, it's going to hit that second ball. Okay. So in order to conserve momentum, we know that they can't both go off to the right, or maybe off in this direction, right? Because momentum would not be conserved. Something has to go off in this direction in order for it to conserve momentum. Now, a special case for elastic is it also has to conserve kinetic energy. Okay? And we know an easy case where both momentum and kinetic energy is conserved, which turns out to be the right answer, which is if this one coming in hits that ball and transfers all of its momentum and all of its energy to the second one. So the second one ends up leaving off in that direction. Okay? I can try to show you that here, but these are not perfectly elastic. Remember that steels, there's sort of about 80%, 90% elastic. So if this were ideal, we would see that. We would see the energy completely being transferred to this one and that one taking off. Okay? You can sort of see that. I should have gotten a little stand for this, right? That did it much better. Okay, but you can imagine this is like that stand. So if this were perfectly elastic, this one would be coming in, stopping, and this one's rolling off with the total momentum and energy of that initial one. Okay, so this is the final state after the collision. We should have that first one at rest and the second one moving off with the final velocity just equal to the initial velocity of the one that came in. So it's completely transferred its momentum and energy to that second ball. Okay. So in this case, the energy is conserved and the momentum is conserved because these have equal mass. So we're looking at balls with equal mass. Okay. Let's compare that with the same collision, but between two perfectly inelastic objects. So okay, perfectly inelastic. So case one, same case. So one of them is at rest. Okay? So we're going to have this one 1 coming in with some initial speed or initial velocity. Hits 2, this one is at rest. Okay? But this is a perfectly inelastic collision. Remember, perfectly inelastic collisions mean that they stick together. Okay? So in this case, we also have the initial momentum. Directed in that direction. Okay? So momentum is always conserved in a collision. So we have to get a momentum out of here which is equal to that initial momentum. Okay? But the final state afterwards, so after the collision, we're in the case where those two are stuck together, okay, and they're moving off together at some final velocity. Okay, so we have twice the mass now moving off to the right, okay, in order to conserve momentum. So our initial momentum was this mass times its initial velocity. This one is now twice the mass, okay, so moving off in this direction. So in order to conserve momentum, since it's twice the mass, it has to have half of the final velocity, right? So this final velocity is equal to 1/2 the initial velocity in order to conserve momentum. Oh, I have a demo of this. Maybe this one will work a little bit better. Let me turn this back on. Okay, so this is an air track, and once again, not particularly well balanced. See if I can adjust this. That'll help. Okay, so these are two masses basically moving on this track. So since it's an air track, this is nearly frictionless. Okay, let's do that first case and see if it works better on here. So I'm going to send this in with an initial velocity. It's going to be hitting this one, which is at rest. And right now I've got two, they've got little bumpers on them, so they will bounce. And let's see if we can mimic that elastic collision pretty well. Oh, that was good. Excellent. Okay, so you can see it's going to transfer all of its momentum and energy to this one, okay, and stop. Okay, the energy is conserved and the momentum is conserved. Now, if I flip them around, these ends have magnets on them, so in theory they're supposed to stick together. Okay? So this is forcing it to be a perfectly inelastic collision, if it works. Let me try that here. So this one's at rest. This one I'm going to be sending it in with initial velocity. Okay, you see they stick together, and they're going to be moving off to the left with half of the initial velocity of the first one coming in. Okay, I'll do that one more time. Okay, so let me turn this off for 1 second so you can hear me. The momentum was conserved, so it moves off with half the initial velocity in order to conserve momentum. Let's look at the kinetic energy, though. Remember, kinetic energy feels like the jury's coming in when you guys come back in. Starting else. Kinetic energy is equal to 1/2 the mass times the velocity squared, right? That is our kinetic energy. Okay? So let's just think about that. So we have the initial mass coming in. It's got its initial velocity. Now, if we look at that, after the collision, we're going to have twice the mass. Okay? But in order to conserve energy, it's moving off with 1/2 the velocity. So we've got 1/2 velocity. But that's squared, right? So we've got a factor of 2 coming in because the mass is doubled, but we've got a factor of 1/2 squared coming in because the velocity is half, which means that 1/2 of the kinetic energy was lost in this collision. Okay? From the inelastic collision compared to the elastic collision, half of the energy was lost in order to conserve momentum when they stick together. Okay? So let's think of, actually I won't draw these, I'll just talk about them. Let's turn this back on. Okay, so let's think about so I got the bumpers back on here. We're going to look at an elastic collision. I'm going to send these in towards each other with roughly the same velocities. Okay? So opposite directions, so they both got momentum. Okay? But if the momentums are equal, right, then you've got this momentum plus this momentum, which is equal to 0. Okay? So the total momentum for the system is 0, but we're still conserving energy for the elastic collision, which means stuff has to be moving afterwards. So in this case, if they come in with the same speeds, okay, they're just going to perfectly, this one's going to transfer all of its momentum and energy to that one, and this one's going to transfer all of its momentum and energy back to the other one. Okay, and they're just going to rebound, perfectly bounce off of each other. Okay, and very intuitive as well, I think, the other case. So now they're going to have an inelastic collision, so they're going to come in, they're going to stick together. This one has momentum coming from this direction. This one has momentum coming from this direction. Okay, they've got the same mass and the same speed, so those should be canceling out. Okay, when they come in and stick together. Okay. The final momentum is 0. The initial momentum is 0 because they're canceling each other out. But all the kinetic energy was lost in the collision. Okay. One more example, just to give you guys a little bit of intuition. Let's say we're going to send them in towards each other again, but this one's going to have a very small velocity, and this one's going to have a much higher velocity. Okay. So that means we got a little momentum in this direction, we got a lot of momentum in that direction. And so in order to conserve momentum, we're going to have this one shooting off with a larger momentum to that side, right? So once again, in this case, they're just exchanging them. This one's going to give all of its energy and momentum to that one, and vice versa. So let's go ahead and do that. Right? So I think that's a pretty intuitive case. Let's do it one more time. I'll give this a small velocity and this one a large velocity. Transferred it all. Okay. And in the inelastic case, these are going to be sticking together now. You've got a small momentum from this side, a large momentum from that side, which means when they collide, they have to both go moving off in that direction in order to keep the momentum conserved during the collision. So we got the small, the large, okay. And they move off with the same momentum as they initially had, but they've lost a significant amount of the kinetic energy since they're moving together. Okay. Those were examples when we've got two equal masses colliding. I want to look quickly at one more example, which is if we have a collision with a very massive object. So you have a lighter object that is colliding with a very heavy object. So you can think of throwing a tennis ball at a train or something like that. We've got a very light object and a very heavy object. So let's look at what happens in a collision like this. Okay, we'll look at two cases. So this is a collision with a massive, and specifically a massive moving object. We've already seen what a collision with a non-moving object is. That's just something bouncing off of a wall. Okay, so a moving object. So we have a little mass. Let's call that M1, a little mass 1 that's moving in and colliding with some huge, much larger than mass M2 that's moving with some speed. Okay. Easy case, perfectly inelastic. You've got a very large mass coming in and hitting that very small mass. So let's imagine this is your car. This is the fly hitting your windshield. Okay. So very small mass hitting a very large mass that's moving. Okay. We know what's going to happen in the perfectly inelastic case. The final is just going to be your car, M2, with that little mass, M1, the bugs stuck on it, okay, moving off with the initial speed the car has. When you hit a little bug, it doesn't really change the speed of your car very much, okay, or at least it's insignificant. Perfectly inelastic case, that's very easy. Okay. Let's look at the elastic case now, which is a lot more fun. Okay, so an elastic collision. Okay. Since we're running out of time, let me do the easy version of this. Okay? And if we have time at the beginning of next lecture, we'll do the harder version. Let's say that you've got your massive object, maybe your car, and it's moving with some speed, v2. And we've got this mass that's just sitting there at rest, a smaller mass at rest. Okay? And these two are going to collide elastically. And we want to know what's going to happen to that mass, to both of them afterwards. Okay? If that's sitting there at rest, then that's the easy case. If it's moving with a velocity, it's a pretty small change in that. But let's look at this case. Okay? So this is very easy to understand if you change your frame of reference. So let's change the frame of reference from us standing on the ground watching this collision to us sitting in that car watching this collision. Okay? So from the car, frame of reference. Okay, we've got that, if you're riding in that car, there you are, minding your own business. In that car frame of reference, you're at rest. You're just sitting in your car. Okay? It might be moving on the ground, but in that frame of reference of the car, you're at rest. And this frame of reference, that ball is just moving in with that speed, v sub 2, which the car has from the ground. So that ball is approaching the car with that speed, v sub 2. It's elastic collision with an object at rest. We know exactly what happens to this case, right? Afterwards, that ball is going to be shooting out. Okay. It's going to rebound in this frame of reference with v sub 2 in the opposite direction for an elastic collision. Okay? So, but now this is the frame of reference of the car. Now remember that that frame of reference is moving on the ground in this direction. Okay? So if we want to go back to the ground frame of reference, right? If we go back to the ground frame of reference, then everything in that picture is moving to our left with the same speed that the car had initially, v sub 2. So from the ground frame of reference, we've got the car, once again, hitting that small object didn't really change its speed. It's moving off with v2. But now that mass, m1, is moving off with not just v2, but v2 plus v2, because we're moving to the new frame of reference. So twice v sub 2. So when an object, a small object, bounces off of a moving massive object, it picks up twice of the speed that that massive object has in that frame of reference. Right? So if there's a train speeding towards you and you're feeling brave and you Want to stand there and throw a tennis ball at it? Okay. You better be careful because that tennis ball, when it bounces back, not just has the initial speed you threw at it, but it picked up twice of the speed of the freight train that's moving towards you. Okay? You guys will want to see this demo. Okay? So before you start getting your stuff ready, let's do 2 examples of this. Okay, let's see. Can you zoom down on here? That's good. Okay, what I have here are a bunch of bouncy balls, all on a little stick. Okay? Massive to less massive. I'm going to drop them, okay, and what's going to happen is that they're going to rebound, but that means that the top ones are going to be rebounding off of the bottom ones when they're bouncing back, which are much more massive, okay? So if I drop this a little bit, we've got a small object colliding with a much heavier object, okay? Did you guys see that? Let me do that one more time. Okay, you can see that they picked up a lot more velocity than when they would have got just from bouncing off of the ground. I should have done that a little shorter. Okay, same. Okay, here's the demo you can do. You ready? We've got bouncy ball. You guys might be prepared to catch this. We got a basketball and a little bouncy ball, okay? I'm going to drop them. When they bounce, the basketball is going to rebound. It has a much larger mass, so it's going to be colliding back with the bouncy ball, okay, with a large mass object going upwards in the opposite direction. You can see it rebounds much, much higher than it would have otherwise. Okay, that is it. Want to see that again?